Yes. All right. That's good. All right. All right. So what I was saying. So see, so this is 223. Let's get there. Let's like here or something. No, it's too far. Oh, that's a Rouse model. No, I don't think you can. You mean like find? I don't think you can do that. Maybe you can. 223. This is crystallization. See, there's nothing about crystallization in the Colby Rubenstein book. This guy has a whole chapter. So it's solid state. And then he does, so when he starts talking, and then it's physics. So when he starts talking about
the solid state,
yeah,
it's a solid state guy.
solid state physicist. Yeah, so when he talks about dielectric response. So it's like that's from ceramics, right? But also when you do it, you can do it. So these oscillatory measurements. So you do it with a viscometer, with a Conan plate, and you can put a clamp on it and do a tensile too. So that's called dynamic mechanical, and then this kind of what's it called? Low amplitude shear measurement. So you do an oscillatory shear measurement. I think it's low amplitude oscillatory shear measurement, with the viscosity, and then you can also do the same thing like that. And then instead of doing mechanical, you can just put a dielectric, just put a charge across it, and then look at the dielectric response. So you can just change the voltage across it and then observe the polarization of the material, get the dielectric constant, and that's got a real and imaginary part too. You can get the same relaxations from electrical or from mechanical, and it's easier to do the electrical because you don't have to move anything. So you have to worry about grip slip or anything, and then you just turn a knob to get the frequencies like a radio. It's not. So the dielectric has some arguments to be made that that's a better way to do, and you get basically the same kind of relaxations from it. But I mean, it depends on the polarity of the material. Like in other words, it's going to respond to electric field because it's polarized. The molecules are polarized. So it's got different response than the mechanical in a sense. Like you're probing a different thing, but you get the same thing. So all this dynamic stuff. Anyway, the math from all the dynamic stuff came from ceramics, like the whole Kolkol plot and all this stuff about Maxwell model and things that kind of came from ceramics dielectric measurements. And if you're a physicist working in polymers, you kind of would take it from. There's a book, there's an original book. I don't have it on here. It's from the 1960s called Inelastic Response of Polymers, something like that. I forget the guy's name who wrote it. It's a famous book though. I have a copy of it somewhere, but it's anyway, it's all just about dielectric relaxation. But that book was the foundation for all this oscillatory shear and everything else. It's all the math came from this dielectric response stuff. So when Strobel talks about it, he talks about the susceptibility, dielectric susceptibility is alpha, and that ends up being like the modulus in a mechanical test.
Okay.
So it's like you have, like for transport, you have fluid flow and heat transport, and they're like equivalent equations, right? Everything's the same. Same with dielectric and mechanical. Like you can just use the math from one and pop it into the other. So Strobel takes it from that perspective, and he just talks about the kind of the dielectric response through everything. He calls everything susceptibility. And so there's groups of people, if you're coming from a physics perspective, then everything is susceptibility. If you're coming from kind of a mechanics perspective, everything's modulus. If you're coming from this rheology, like chemical engineering, everything's a viscosity. And they're all related to each other, like they're kind of inverse to each other type thing. So the language can get a little confusing, and the approach can look like they're talking about something completely different, but it's all the same thing, So there's a lot of reasons why this area is a little bit.
But why is it so? You're looking at it from the different language, but then the whole idea is same.
It's easier to understand from a dielectric perspective. I think that's true. And then the susceptibility is really the compliance. It's not the modulus. So it's one over the modulus. So if you have a complex number, then you have to do it. So you have like a number plus I times something, right? So you have to do the inverse of that. So it's not just the inverse of the thing. You have to get rid of the I in the denominator and put it in the numerator by multiplying by the complex conjugate. And then you can get it to be from compliance to modulus. So the stuff has to be kind of inverted. Anyway, the math becomes kind of goofy. Like there's a lot of math to it. That add on to that all these scaling relationships, and then it's pretty messy, you know. So anyway, so this is a Strobel book. You can see I use this slide, right? The response function. So that comes directly from dielectrics. So you say that the thing, like if you could pulse the thing, like if you hit a bell with a hammer, and then it's going to oscillate. So that's the response function of the bell. But you could think that if you're in an orchestra or something, you're pounding the bell all the time. So there's a lot of different things, and you dampen it sometimes. So there's a lot of different things hitting it, but the response of the bell is always the same. So there's some feature of it, this kind of natural feature that's a response to a delta function, like a pop, and then how it responds. So liquid, you pop it, it moves. It doesn't, in a solid, you pop it, it relaxes, it's elastic, boom, bang. And then a simple relaxer, you pop it, and then it relaxes down. So if you want to know the response over time, you're going to take an integral of that response function times everything that happened to it will give you what comes out of it. That works with dielectrics, it works with compliance, it works with modulus. So that's called superposition. Like you're going to take, well, that's not superposition. That's just the way a response function works. Superposition means that you're going to have different response functions for a material. So you're going to add up the response functions to get the total response to the system. So Boltzmann's superposition principle, you can break down into elemental responses. Like in other words, this is going to have exponential minus t over tau. So it's got a relaxation time. You could have a bunch of relaxation times, like a relaxation spectra. So you can have, in other words, you have different chemical groups on a polymer, and the different groups are going to have different relaxation times. Like the side groups can spin, the main chain can go through an accordion thing, or it can shake somehow. However, it's going to move. Each of those has a relaxation time, so you're going to integrate all those and get the total response of the thing. It's going to be a sum of the response functions for each of the components. That's the Boltzmann superposition principle. You can sum up the components of it. So anyway, so there's a bunch of things like that go into this. Anyway, first, yeah, I want to just go through the homework first. Let me get rid of this thing. Hide the floating controls, get rid of Daniel. Daniel, can you hear me? Hopefully you can hear me.
Yeah, I can hear you.
Oh, great. All right. Let's see, the homework. Yeah, so I mentioned that homework, I put up homework 9. That didn't help me. Here it is. All right. You can see it. I can't see it. Yeah, that guy, right? That's not what I wanted anyway. I wanted the paper. I guess I need both, but all right. So let's see. What did I ask? Everyone did this. Okay. Half the people got this wrong. The advantage of shear versus tensile. That's a fundamental thing. That's why Mooney-Rivlin, why that thing exists, that weird plot. Right. So if you pull on a piece of metal, so when you pull on a piece of metal, let's see, or ceramic, right, then you're going to get this stress strain thing, and it's linear. Like it goes from 0, 0. Oops. Oh, this thing's all messed up. I can see it now. Yeah. Right. So you get that, right? And then you'll get, so then it's, let me make it steeper. So it goes like that, and then it's going to yield. And then sometimes you can get a something like that, right? So that the stress remains constant. That means when you get this region, we have non-uniformity. So that in polymers, that would be a neck forming. So you have your thing like that, and then it forms a neck. So it gets narrow here, and it's like that. And then all the action is right there, and that eats into the thing in a polymer. And a metal, that usually happens because you have shear planes, right? That happen. The thing defects form in the metal, and they slide. So you get that, and the yielding is the initiation of that. So there's some kind of energy. That's an energy for this phenomenon to start happening. There's an energy barrier for it to happen. Once you get to that energy, so the stress times strain is energy. That's the energy to start either slip planes or whatever is happening in the polymer here, which is you're kind of forming fibers. Right. So anyway, but this part's the part that you're interested in because it's linear, right? And in that part, none of that stuff is happening. You're not doing any weird deformation thing. So in that part, the atoms are just separating, like the atomic spacing A goes to A plus delta A. The stress actually increase, so that in doing that, the volume changes. That's called dilatometric strain, or dilatometric response. So like dilation, like you put dilation in your eyes and makes your pupil get big or something. Right, so this means a change in the volume. Your eye doesn't change volume, but basically dilatometric means a volume change. So, but if you have a liquid, right? So if you take liquid propane and you put it into a piston, right? And it's at 1 megapascal. That's a tank of propane that you burn. It's like 1.2 megapascal. And then I decrease the volume of that by 2%, right? The pressure goes from 1.2 megapascal to 60 megapascal, 600 atmospheres by 2% volume change. If you do the same thing with a gas, nothing happens. The pressure doesn't change. I mean, it's just PV. It's just proportional to a 2% change. So if you go from 1.2 to 1.4, right? So this is a liquid is incompressible because of that. Like if you try to compress it, the pressure goes through the roof, right? And a polymer is a liquid, a rubber or a gel is a liquid that's got the ends connected together. So it's the same as a propane liquid. You just glued together the ends of the propane molecule and made it into a kind of a jello, right? So if you try to compress that thing, you won't be able to, because you can't push 60 megapascal. It's too much for you to push with your hand, right? So anyway, anyway, it's an incompressible material. Polymers incompressible. Human tissue incompressible. Everything is kind of like a liquid is incompressible. Everything is kind of, you think of as a solid, it's compressible. Like when you take a piece of metal and pull it, the atoms actually, at the early stages, this is like 0.2 strain, right? It's like a low strain, but at the early stages, you're just actually pulling the atoms apart, right? And there's no hierarchy to the structure. In other words, when you go from the atoms, then you go higher, it's made up of all atoms. You go higher, it's all atoms, right? It's the same. It's a single crystal. It goes all the way from an atom to macroscopic. Same thing. So you pull on the big thing, you're pulling on the little things. Polymer isn't like that at all. It's got like the persistent unit, it's got some chemical unit, persistent unit, then the chain, and then some networking, and then who knows what happens. So there's many steps to getting to the macroscopic thing that you pick up. It isn't just one connection, right? So anyway, so it's not going to have this simple behavior, and it's going to be incompressible because it's basically a liquid that's glued together. So it's a liquid, it's incompressible. So dilatometric strain, you can't get any. You can't get any change in volume, right? So because of that, then lambda 1, lambda 2, lambda 3, the 3 that has to equal 1. Like you always have. So if you pull it in the x direction, then these two respond back, right? And then you won't get this kind of curve. You'll get the thing will continuously curve. There's no place where it's linear at all, right? So you can't get that fit. So if you analyze this, you take the strain tensor and then you find the invariants. You have like I1, I2, I3, and I3 is this thing. So that's I3, the third invariant. In other words, if I change the coordinate system so X swaps with Y and Y swaps with X, I still get 1 for that. Like that's why it's an invariant. It's invariant to coordinate system rotation, any rotation, right? So, and then I1, I think is a 1 over lambda 1, or I2 is 1 over lambda 1, whatever, and I1 is lambda 1 squared plus lambda 2 squared or something like that. So anyway, so you got that's all continuum mechanics. Like that's books written on it. Like you'd have to read really boring books to figure out what's going on here. Like it would take you a long time and it's kind of worthless. But in the end, you can't make that plot for polymers. It's useless. You can do it to see like kind of what it looks like to pull it, but you're not going to get any information out of that plot, right? So the plot you need to make is this: take the stress, divide by the strain, minus the strain minus 2, and then plot against 1 over that. And then the slope of that thing is going to be the second invariant, the sum of the 1 overs, and the intercept of that is going to be basically the modulus. That's going to basically give you the kind of the tensile modulus, like the Young's modulus of it, and that's the way to get it. And the reason that you're doing that is because it's incompressible. I mean, it seems weird to think that something like steel is compressible and something like Jello is incompressible, because you think that steel is stronger than Jello, so it's got to be that the Jello is compressible. But if you take the liquid propane and put it in a tank and try to change it by 2% volume, you find out very quickly that it's incompressible. In order to do that, you have to have a huge amount of force. Yeah, so it's totally incompressible. Anyway, so that's the first thing. Yeah, that's number one. I hope that goes home, because that's kind of like repeated kind of misunderstanding in the literature of people, right? So it's important to kind of get that picture. So also that's why you would use a shear measurement, because you're not putting, when you do shear, there's no dilatational stress put on the material. You're sliding it. Like you take a deck of cards, you're not separating the cards. There's no volumetric change. You're just sliding it. When you slide something, you don't change the volume. That's the thing you should do with polymers. And if you plot the stress versus strain for a solid polymer and under shear, it's going to be a straight line, and the slope is going to be the shear modulus. That's a number. You know, you can measure it from that plot, right? So that's a measurement you should do naturally for polymers. The only reason to go to the tensile is if you're, I mean, if you have some application where that's kind of what you're doing, like if you're stretching rubber bands, that's a tensile thing you're doing. Or like if you're chewing gum or something, or you have like a rubber thing to cushion shock or something like that, and you're doing a tensile, it's a one-dimensional kind of deformation you're doing. So anyway, so in those cases, then you'd need to use a Mooney-Rivlin to understand kind of what's going on. You wouldn't do the stress strain plot. So, but nonetheless, everyone always shows stress strain, because that's what the instron spits out for the thing. Everyone got that, I think, mostly. I mean, Nichols talked about why time of flight's advantageous. I mean, it's basically you get a better resolution. It's not obvious why it's better. In general, like coming with in any kind of experiment, you usually want to have a really clean setup. We have a clean, like a single wavelength, right? I mean, it's nice to have a single wavelength and everything's simple, right? And time of flight is really complicated, because it's relying on a lot of assumptions when the measurement's made. Like, did you convert from time to energy properly? You know, there's a lot of algorithms that are going into it. And also, if the energy is changing, so the absorption coefficient changes with the wavelength, with the energy significantly, because huge changes in it. So you have to measure. Not only do you have to measure your sample measurement as a function of wavelength, you also have to measure the absorption and the noise changes. The background noise changes with wavelength. Like everything changes with wavelength. So every wavelength you pick out of that time slice that you take, it's a different measurement. It's on a different instrument. You can't assume it's the same instrument when you're at 1 angstrom and when you're at like 10 angstrom wavelength. It's not the same instrument anymore. The background's changed, the angles all change. So anything is like, say you have some artifact and it's reflecting off something, or it's diffracting off the window or something. So all those things change. So it means if you really want to analyze the data from a time of flight, you'd have to have like, so you have a matrix of all the measurements you're making in angle and also in time, right? So you'd have to have this huge matrix. Your data set would be so enormous if you actually analyzed it properly. So you have to shortcut. It's not as simple as a one wavelength measurement from a reactor. Okay, so anyway, so that's kind of like people like it because there's a lot of flux. So it's a big bang for your buck kind of thing. It's not a nuclear reactor, so there's no possibility of a meltdown. It generates a lot of radiation, and there is radioactive waste from it, like a reactor. But in general, like you're better off with a reactor, almost always, except sometimes people make the argument that this thing's better, I guess is what it comes down to. And maybe they're right, but it's pretty hard to tell given it's so complicated. I guess you have to believe them, you know. So they say that you get a better resolution of energy or something with it. Anyway, the real reason that we have time of flight instruments is because people didn't want to build nuclear reactors because there's a lot of baggage with it. You know, there's a huge amount of baggage with nuclear. I mean, from the point of extracting uranium, so there's never been a reclamation of a uranium mine ever in the world. Any place where uranium was mined, that's a wasteland. Like if you go to Arizona and the Navajo reservation where they got uranium for the bombs, that's still yellow dust everywhere, still radioactive. That land's dead forever. And to reclaim it, it's too much money. It's probably the same in Chad and Niger in Africa. Right?
Yeah.
Like the places where they mine it, that's dead forever and they'll never reclaim it. So that's the starting point of it. And it goes on from there. It gets worse and worse as it goes on. So finally you get to meltdown and then, you know, it's kind of like, or nuclear weapons. It's like, you know, is it really worth it?
I guess it's because of the active nature.
It's a huge amount of energy you can get, you know. So this small nuclear plant, so that the largest coal plant in this area is this Zimmer plant, which they just shut down because they're getting rid of coal altogether. Not because it's too expensive, not because they want to save the earth. So, but that plant was originally designed as a nuclear plant, and they converted it to coal. So it would have been just one reactor would have produced as much as like, so they burned. Did you go on a tour of that place? You went to the other one.
Yeah,
but the Zimmer one is like 10 times as big as that one.
Yeah, this is.
Yeah, so basically that thing was burning like 4 barges of coal a day or something, 4 barges an hour, a huge amount of coal going through. And the one nuclear plant, just a little thing, you know, producing that same amount of energy. There's a huge amount of energy in it. It's incredible, the amount of energy. But I mean, there's something that goes along with it, you know, the problem. So it is like an amazing energy source. But I mean, anyway, so both things have problems. Spallation, so people don't want to do that. So the spallation is what people ended up with, especially politically, I guess is what happened. So they built a few spallation. The first one was at Argonne. The first one that was really functional was at Argonne National Lab. And it produced a lot of papers, but it took 25 years for it to get to be functional from when they built it, because of all these nuances to it. So by the time they got it to be functional, they had about 2 years of operation and they retired it. Yeah. And they were putting out, and the reason they retired is because they built a new one for $1 billion at Oak Ridge. And then that machine that they had built for like maybe 10 million or something at Argonne, smaller, was producing like 50 or 100 papers a year, each instrument. And the new one that cost $1 billion was putting out like 1 or 2 papers a year. So because it takes 20 years for the installation to get online, so anyway, so who knows? That's kind of politics of it, is what in this whole field, because it's big money and it's like radioactive stuff, everything's politics. It's pretty crazy. So what's the advantage of time of flight? You could say like it's politics in a sense, Stretch exponential, I think everyone got that. I mean, this was like your opinion. And then this thing. So if you see -2 and you have time and size, so power 2 or power 1/2, then you just have to immediately say Brownian motion. That's the magic word. So power 2 or power 1/2, and you have time and size. Q's inverse size. That's Brownian motion. That's all there is to it. I mean, that's diffusion equation.
I guess because we do mention the
You have to say Brownian motion, or you could say diffusion, but Brownian motion's better because that's really what it is. So I don't know. I think that you always see any kind of dynamic measurement, and you're going to see this thing, and it's going to come out like time and size, and it's going to be 2 or 1/2. And then you just have to immediately say Brownian motion. Then you're right, And that's the only touch point except for power 1, time equals position, and that's ballistic. So there's only 2 things that are natural in that whole realm, Then everything else, it's either subdiffusion or superdiffusion, right? So this is superdiffusion because ballistic moves faster than Brownian motion. And subdiffusion means even though Brownian motion is slow, you're going even slower. Like the -3 means you're even going slower. It means something's interfering with Brownian motion. So what could that be on a molecular scale? It's like the network or something, some kind of chains hitting each other somehow. So it's saying, he says Zim model. So you can probably just say something stopping the Brownian motion, hindering it, slowing it down. And then this thing, I guess I had a real hard time understanding his arguments, and everyone else seemed really happy with it. So some of you guys are using the chat GPT to answer some of these things, like question 1, I think, or one of the questions. I mean, I guess it's okay. I mean, I looked at it. I know you didn't write it because you can tell it's using words that you don't use, I mean, that's obvious right off. But then if it goes wrong, then I take a lot of points off. I try to take some points off if chat GPT made a mistake and you didn't recognize it. Because it's a computer, if you don't know, you can use computers, but basically, if you don't know when it makes a mistake, that's when you're going to really have a problem with computers, Like, yeah, it's like the Tesla driving itself. It's fine all day, and then one time it's like
use a computer to look for the question without that.
easily, yeah. Chat GPT gives a pretty good answer. One group did it for sure.
For the question 1.
Yeah. Oh, question 1. No, not question 1. Question 2, time of flight. Yeah, question 1, you have to do the Igor thing. Yes, you couldn't do, but you could, they did go to this question and they didn't get the right answer. So I took points off for that. Like they did answer that with chat GPT. It doesn't give the right answer. So it doesn't know, apparently. Maybe then probably means the world doesn't know or something. Majority of the world doesn't know. So, and then this one people answered, but you run into the problem, how is it advantageous for this measurement? And it can't answer that. So it can answer the other parts, but it can't answer some specific things. And it's pretty obvious why it can't answer it. And then they're using chat GPT, so you just hack them for points on those things. That's, it's okay to use it, I think. I guess I'd hope that you would answer it yourself or use it. You might use it first to give you, so you're in the ballpark, and then answer it yourself and see which one's clearer, like how is it that it's clearer than what you did? And it has an algorithm that's using, like you say, what's this compared to that? First it defines this, then it defines that, and then it finds out like what's the connecting point between the two and gives a paragraph. I think it seems to always answer that way. And that's a pretty logical way to answer something.
What was the difference between?
Yeah, what's similar between dogs and cats? Well, dog's an animal that walks around with 4 legs, a cat's an animal that walks around with 4 legs. They both have 4 legs, you know? I mean, so that's the algorithm that seems to be using. I'm not sure, but that seems to be how it works, but that's a good algorithm to use when you answer questions. Like something you don't really understand what's going on, but you know what A and B are. So first you list out what A and B are, and then it's a logical sequence to say what's the similarity between A and B. Unfortunately, in this thing, comment on the advantage of shear versus tensile, if you had said this is shear, that's tensile, it doesn't give you the answer because the answer has to do with continuum mechanics, and it's not giving you, the question didn't have continuum mechanics in it. Or if you had put in like dilatational into the question, it could have answered it. If you said like which one has dilatational stress, it would answer that. But so somehow it's missing. It can't make the next jump over to, it will someday, but basically if I corrected it, then it would do it next time, I guess. All right, so that's that business. Then let me open these things up. So okay, so I want to go to slide 12 here. Nope, maybe it's slide 12 here. Yeah, that's good. All right, so that's up there, right? Yeah. All right, so let's see, let me just do this. Anyway, in the paper for Friday, it talks about Maxwell model, right? So you have two, let me go over here. I didn't put this in, but there's two models from the 1800s for mechanics, right? The Voigt model, which it's always been called the Voigt model. And like in the past, I'd say like 1990, maybe 2000, they started calling it the Kelvin model. And then if you look it up in Wikipedia, it's like the Voigt-Kelvin model. I think it's the Voigt model. Voigt's a German guy. Kelvin was Lord Kelvin. Kelvin's got plenty of stuff. He doesn't need another model. So basically they're both made up of what's called the dash pot and a spring, right? K spring X the force. And this thing goes with dx dt times the viscosity is the force, or times the friction factor if it's a molecule. And this is the modulus. So it's either the modulus, so this would be like modulus and viscosity or spring constant and friction factor. Right. So, and this would be stress, and this would be like strain, like gamma maybe. All right, so anyway, you can do it either for bulk materials with modulus, or it'd be shear modulus and viscosity, or you could do it with spring constant and friction factor, right, if you want. And then it's the same. The Voigt model is like a parallel model, and then the Maxwell model's the series model. So this one is going to be like flow because, right, so you have a spring damping flow. Right, in other words, this thing, if you pull on it, eventually it'll just keep going because it's got a viscous element in it. It'll keep flowing. Whereas this thing, these are hooked together. If you pull on it, it'll eventually reach spring because the viscous just damps the spring. So this is like a shock absorber, actually, in a car, right? So you have, it's got a spring, so it's like you can have a spring coil suspension, and you can also have a shock absorber. A shock absorber has a viscous element that dampens the spring action, smooths it out, right? So the Voigt model is basically a damped shock absorber. And this thing I don't think exactly exists, right? Unless you look at this in terms of capacitor and resistance. So this can also have an electrical analogy, like capacitor resistance. They both systems would end up with a time constant. So because you have dx dt and x here, you end up with dx over x, and the other side has dt. When you integrate it, that gives ln. This gives t. end up with exponential of something to the t over tau. And ends up tau as a modulus of the viscosity. Or tau could be the friction factor, the spring constant over the friction factor. Right, so I think it's the other way around. I'm not sure I got that right, but anyway, so that's the idea of both these models. This one ends up with 1 minus e to the minus t over tau. Right, so at long time, this goes to 0 and get 1. It's kind of like the modulus in the end. So this thing ends up being a solid. And then this one ends up giving you e to the minus t over tau, just that. And then it's like e over viscosity as a prefactor equals the position. So that means you just have this kind of decay. That's a relaxer thing, right? You have the position and time, and it just decays down to 0. That's flow. It ends up flowing, and it's got a spring in it that kind of dampens the flow. So on short times, at short times, this thing is solid, and you just get a spring response. For long times, you get it. Sorry, in this one, at short times, this is solid. You get a spring response. At long times, you can forget about the spring response and just have flow. So it flows in the end at long times, and in the beginning, it's a solid. That's a viscoelastic fluid if it ends up flowing. So if you're doing fluid flow, which is like Rouse model, Zen model, then basically you want to use the Maxwell model. Right. So you'll see in the paper, he said, and everyone says like, oh, it's a Maxwell material. So what does that mean? You know? So in physics, in Strobel and also in the Doi book, he talks about the dumbbell model, which is the Maxwell model, or Strobel calls it a simple relaxer, because in dielectrics we call it a simple relaxer. Like you put a charge on it, and the charge decays with time exponentially, and it's got a relaxation time. It's like a capacitor and a resistance, right? So it's the same model. So you end up with the same equation. It's exponential t over tau, and that's the tau. And if you look at it from, oh, sorry, yeah, right, might be better off not seeing it, but anyway. So if you look at it, if you add in this fluctuation GT, it's like this is like KT pushing the thing, push and pull, then that ends up Brownian motion with a damped response, this exponential decay. So you push, decay, push, decay, push, decay, push, decay. So these are just random push from temperature, KT. Just GT would be proportional to KT. Then it's just showing that exponential decay response, which is called a simple relaxer, right? So anyway, how can that get more complicated? Well, if you want to say, all right, so I have this is in time, right? And then I want to convert that to frequency. How do I do that? Well, so you have your nice simple time response, and you want to have a nice simple frequency response. So to get that, you Fourier transform from time to frequency, converts time to frequency, and you have an imaginary part because, so in terms of modulus, this is imaginary. The flow is imaginary modulus. And in terms of flow, this is imaginary, like the solid is an imaginary flow. So that's how they relate to each other. They're like, it's almost like the magnetic and electric field from electromagnetic wave, like one's kind of imaginary to the other. Because you can convert energy from flow to spring or from spring to flow. You can store the energy in spring and it can release and flow, or you can store it in flow and release in spring, like depending on if you're in Voigt or in Maxwell. But we're in Maxwell, so it'll be spring converted to flow. Like the energy is stored here, by stretching it, goes back into that and releases its heat. Right, so that's the idea. So anyway, so you have your, this is a function you have just from that kind of simple integration of the derivative thing, because you end up with dx over x and ends up being an exponential response. And I think tau's the viscosity over the modulus. I think that's how that works. But anyway, so you do a Fourier transform of it. So you have Fourier transforms exponential I, and then the two units. So it'd be like Q and R, or here it's frequency and time. So those two cancel out, are unitless. So your units you're going to get out of it are inverse to the units you had here. So you're making inverse space from the real space, which is time. Frequency becomes like the inverse space. Or it could be energy, like frequency and H nu is energy. So this could be converting like time to energy too. you want. Anyway, so that's, you just have that thing times that thing, arguments sum in an exponential, like in a power, and you, like 10 squared times 10 squared is 10 to the 4 type thing. So you add together the arguments, you end up with this thing, right? And then, so then you have t and dt, and you want to get rid of this. So d of this is that times dt. So you have to divide by that to get that to be exponential of x dx. So you have to divide by that thing that's in here, which is there. And then the derivative of exponential is exponential. It's the same thing. So it'd be this thing. So that thing at infinity, so when time goes to infinity, that's 0, right? Oh, and this thing has a negative, so that would have a negative here. And then when that thing's 0, exponential 0 is 1, but it's negative because it's this minus that. So the negatives cancel. You just have the delta J over that. So you do have a nice simple thing for the frequency of it. See what I mean? But you have to go through the math of every step of this thing. It's like kind of a nightmare. So anyway, this isn't exactly how you want to have it, because you want to have the storage. This is the compliance. So you want to have the storage compliance. So compliance is like you have a fixed stress times the compliance gives you the strain. So usually you have like stress equals strain times modulus, and this is strain equals compliance times stress, fixed stress. So you put a weight on something. In this case, it's going to be a relaxer. So it's going to just like drag down. Like you have some kind of gooey jello, you put a weight on it, it's going to just stretch down, exponentially down, right? So anyway, so that's kind of the situation with compliance. The compliance is not a good thing to measure. Modulus is easier to measure than compliance, but compliance gives you a nice simple answer, like straight up, it gives you this thing. So to convert that, you multiply by the complex conjugate. So you just make the plus minus for the imaginary part. Then you have I times I is -1, and it's minus, so it makes it plus. And then you have minus times the first term and plus times that, so that cancels out. So you don't have any I left in the denominator. Then you just have plus omega squared. And then this thing's squared, so you square that, and then you multiply the top, and you get the storage part and then the loss part. Which in this case, because it's compliance, the loss is the storage, and the storage is the loss. Shouldn't have said storage and loss. It's imaginary and real, right? Because they're inverse. So anyway, so you get that business, and you can clean that up by multiplying by tau squared. So you get tau squared omega squared, and you have to multiply this by tau squared, you get tau j. And then same thing here. So you get tau omega. Let's see, what do you do here? Here you have tau squared, multiply tau squared omega squared. That's the same for both. And then, yeah, you just, because you have omega here, you end up with tau omega for the loss part. So that's your real and imaginary part to the compliance that you would get. So what does that mean? So if you do a dynamic measurement, this is what it means. This is the Maxwell model. So in the paper, he says, oh, it's obviously a Maxwell model. What he means is this, like he measures the modulus. You'll see it's the same answer for the modulus, but so it means you have this decay, or in the case of modulus, it goes up to the plateau, like the rubbery plateau, right? So you have, and then there's a flow part and a rubbery plateau part, right? So you get, it would be the upside down of this thing, and this thing's the same. So you get, for the loss part, you get a peak, because for this part, you get this decay, because when you go to higher and higher frequency, then this becomes larger, right? At low frequency, it's 1, so you just get tau delta J. And as frequency goes up, then this gets larger, so inverse to that gets smaller, and it decays down. And finally, it's just this number, which is like kills off that, and it goes to like 0. Right, so that function is your normal behavior, which follows the Maxwell model. Like the original thing was the Maxwell model, you get to these kind of crazy equations from that, right? So then this one, in order to understand this, and this is directly from Strobel, if you divide by omega tau, and you have 1 over omega tau plus omega tau, if you take, you're going to plot log plot, or a log plot here on the x-axis, like a semi-log. If you take 10 to the log of omega, because it's 1 over, it's negative of that, and this is positive because it's just omega tau. So this thing has symmetry, and at either end, if you go to small omega tau, this gets large. If you go to large omega tau, this gets large. In between, when you equal tau, when it's 1, 1, then you basically just get this peak in the thing. So it decays down either end of it, and you end up with a symmetric peak. Looks almost Gaussian, right? But it's this Maxwell model. It's a simple model. When you convert it, you end up with these two curves. So that's what he means by Maxwell model. The other thing about Maxwell model is it gives it, so it's you're talking about a system that's got one single relaxation time, like a perfect relaxing system, right? So it's got a single relaxation time. Complications to that would be like you have multiple relaxation times, like you have all these different things going on that absorb energy. So you need to use Boltzmann superposition. Or something else might happen at high frequency, like it converts to a different regime of behavior. It's not a simple relaxer anymore. So then those would be deviations. So how do you tell if you have deviations? Well, you do a Cole plot. So turns out you can take this equation and if you rework it, you can get it to be in the form x minus, so x would be the loss and or the loss, and then y would be the storage. So you have, or x would be the storage, y is the loss, and then you have a shift factor a, and if it's a circle, so say a and b are 0, then you'd be on the x-axis 0, 0, and then r squared would be like the thing that it equals is the diameter, the radius of that thing. All right, so if you rework this equation, you can find out that the radius is the relaxed compliance to the unrelaxed compliance difference. So relaxed minus unrelaxed is delta J squared over 4 is the radius of this thing. And then there's two terms, X and Y, to this thing, which are the storage and the loss compliance. So this ends up being a circle. This center is the offset of the storage part of this thing, which is this 2 delta J, I guess. That's the offset part of that curve. So anyway, it ends up being the equation for a circle. And then you can make this plot of loss versus storage and get a circle. That tells you that that's, when you see that, if you do that plot, which is easy to do, then you see that that's a simple relaxer. It's got a single relaxation time. It's a simple system. So the one reason to do this is to say, is it or is it not a simple relaxer? What is the delta J? Like what's maximum and minimum of the compliance in this case, but it can also be modulus. And then how does it not be a circle? So it shifts over because you have this 2 delta J that should match the radius. And then so each point on here comes from a plot like this. Each point, so you take one point at one frequency, a point at a frequency, and you're plotting this loss against the storage. So each point is from a different frequency. So there's no frequency in this plot, but each point is from a different frequency. The high frequency end is over to the right, and the low frequency is to the left. That's kind of how it works. So basically, if you figure out where the high storage modulus and the low loss modulus are, then you find out that that's high frequency at the right end. Anyway, so then you can have a shift, like it can shift down, it can shift up, and you can have like a tail over here at high frequency where things are breaking down. Like at high frequency, you might run into, in the paper we're looking at, it runs into a network. So like you get a point where loss and storage are proportional to each other, and they're proportional to a power of the frequency. So if that's proportional to that, this is a straight line going up, and that's not going to be a circle. And that means that you have a network. So at high frequency, you're probing a network structure. That's a Winters-Chambon model for this stuff. Anyway, so if you deviations from this, so you just want to see, is it a simple relaxer or not? And if it isn't, you can start saying a few things about it from these plots, the Cole plot. That's one thing. Then since you're easy to calculate the compliance, but it's hard to measure it. So you want to measure a modulus because that's easier to measure. So you take the complex compliance. So in terms of dielectrics, there's always a polarization of materials. There's like a leftover compliance. like the unrelaxed compliance of the thing, which would be the polarization of the material and a dielectric. So when this is done, you like add in a term. You have this term, which we had from here. So we have this term, delta J over 1 over tau I omega. And then I think that's the same. And then you add in this term, this unrelaxed term, to just do it more experimental, I guess. So if you take the inverse of that, and again, you want to get this in terms of an imaginary and a real part, which isn't done here. But anyway, it's possible to convert that. So you end up with a mess, right? So you have to redefine some terms. You say delta is a relaxed minus unrelaxed. So you say the relaxed is that. Then you invent a new tau. This tau from the compliance divided by the unrelaxed to relaxed compliances. And then this relaxed modulus is 1 over the relaxed compliance, and the unrelaxed modulus is 1 over the unrelaxed compliance. And delta modulus is the difference between those two. Right. So you basically take that equation and start plugging these things in, then you can get this equation for the storage modulus, which is like for the shear modulus, which is the same equation. Right. It's the same equation, but it's a different tau. Like tau is related by the ratio of the relaxed unrelaxed compliance. Anyway, you get the same equation. It means you're going to get these same curves, the same Maxwell curves from the modulus, except that the J prime, this goes up instead of down, and this is the same thing. So anyway, so that's kind of part of it here. So he says in this paper he's talking on Friday, he's talking about the Maxwell model. At one point he just says this is the Maxwell model because he shows like this behavior for the modulus. Right, he's showing that same behavior for the modulus. That means it's a Maxwell model. So just loosely termed like the Maxwell model. It means it's got a single relaxation time. And it's kind of a simple relaxer. So anyway, so there's that business. There's a lot to this stuff. It's not particularly easy, you know. So I think you get a hit at it, you get a couple hits at it, and you still won't understand it, and then just keep hitting at it. And if you do it for a living, you'll definitely understand it after a while. And if you don't, then you probably will forget it. You know, so it's like one of those things. So, you know, it's hard to tell. Anyway, it's good to get a hit at this stuff because you'll see it in papers, and then you're going to have to figure out for that paper, what are they talking about? You know, he says like, it's the Maxwell model. Well, I know the Maxwell model is a simple spring dashpot thing. What does it have to do with this? And then you have to go back and say, oh yeah, you have to do all that math to figure out what it has to do with what he's talking about. So that's kind of how it goes. So anyway, in the end, you're going to get, so if you say it long times, the thing's going to flow. You can just say you have that the strain is a compliance times the stress. So tau here, even though tau is used as this tau relaxation time, tau is also the shear stress, like dF dA, with the A being, so it's X and Y, it's a shear stress, like a deck of cards, you're pushing the top card, and this is a shear strain. So this is just that's just the constitutive equation for compliance. And the constitutive equation for modulus is like stress is modulus times strain. So it's the opposite of that, right? And then in terms of what viscosity is, it's the rate of strain gives you the shear stress. And then, or you can convert that to compliance. If you plug in this for that and take the derivative with time, you get dj dt, and you have the tau naught as a prefactor. So anyway, the point of this is to get this relationship for the flow part of the thing. Anyway, yeah, I'm out of time. So why don't we, I'll pick up on this on, well, Monday is going to be like, so next week's spring break, right? So we got Friday, I'm going to go through the paper, and then it's like 2 weeks to turn in the thing on it. You know? Yeah.
Don't come up with a school.
Yeah. So, I mean, you could turn in earlier if you want, but basically probably everyone will do it on the night before or whatever. But so Anyway, so you can do it while you're on the beach in Florida. Sit there and do it. I don't know. Anyway, so yeah, that's kind of cut it off here, I guess. So I'll go through that paper. The paper is long. It's 15 pages, 12 pages or something. It's kind of dry. I couldn't find something that was exciting and also had some content to it. So this thing's got content, but it's not definitely not exciting. But it's from this year, you know, so it is active people talking about stuff. So anyway, hopefully that'll be okay. So all right. All right, so yeah, thanks. Yeah.